and today we're learning about stars. Stars follow many categories dependent on the mass, the temperature, the colour, and the evolutionary phases. Let's start from the beginning. The protostar, the initial phase star, the baby star. And with me, to help me, is my trusty notebook. Now, we need to understand how the protostar forms. We need to understand that it occurs from large clouds of gas and dust called molecular clouds. There's often a misconception that it's nebula, but that's not true. It's molecular clouds. While nebula can be a cause, there are actually usually remnants. Molecular clouds range from 1,000 to 10 million times the mass of the Sun and can span as much as hundreds of light years. They're cold, and that will mean that gas is going to clump. Some clumps can collide into each other or collect more matter. This will strengthen the gravitational force as the mass grows. Eventually, this gravity will cause some of these clumps to collapse. When this happens, friction comes in. It'll heat up, which eventually causes the development of a protostar. Now we have to understand three things about the protostar. Most of the protostar energy comes from heat released by initial collapse, as you can tell, because all that friction will have caused a huge amount of heat. Second, after millions of years, immense pressures and temperatures in the core of the protostar will squeeze the nuclei of hydrogen atoms together, which will form helium. This is called nuclear fusion, and I think nuclear fusion is really interesting. Third, nuclear fusion releases energy. This heats the star and prevents it from further collapsing under the gravitational force, as the heat will provide an outward pressure, an outward thermal pressure, you could say. Stars that are stably undergoing nuclear fusion of hydrogen and helium are called main sequence stars. This is the longest phase of a star's life. In fact, our Sun is going through its midway main sequence phase. And it's dependent on a star's luminosity, size, temperature. And this will slowly change over millions of years. It's how stars work, constantly changing, but it's gradual. Now, what we have to understand about main sequence stars is they're undergoing something called a hydrostatic equilibrium, which is where a star can retain its spherical shape. How is this? How does it retain the shape? What's stopping it from collapsing? Well, I said the balanced inward gravitational attraction from the heat. The heat will balance this inward gravitational attraction that's going to try and force all that matter together, trying to collapse it in a way that will mean that star won't be able to retain its spherical shape. And left out heat will be used as a source of light and radiation, or should I say excess heat. Now, we also know that 90% of the stellar population is main sequence stars. And now we're going to learn about the 10%. Let's go forward. Next, we're going to go into the red giants. When main sequence stars about 8 times less than the Sun's mass run out of hydrogen in the core, it's going to start to collapse, as energy from fusion is the only force fighting gravity's tendency to pull all that matter together. It's going to be squeezing the core, and that will increase the temperature and pressure to a point where helium fuses into carbon. This releases energy. Hydrogen fusion starts to move into outer layers of the star, and this will cause it to expand, or a better word, inflate. The result is a red giant, which is actually more orange than red. and it's in the name, a red giant. Eventually, the red giant becomes unstable and begins pulsating, expands and ejecting some of its atmosphere occasionally. But soon enough, all the outer layers blow, creating expanding clouds of dust and gas, which is known as a planetary nebula. Our sun will become a red giant in about 5 billion years. Now, before we go on to our next star, which is the white dwarf, we're just going to give some key facts about the red giant. Its average temperature is 5,000 Kelvin, and if you don't know what Kelvin is, it's a unit that scientists use to try and get to absolute zero. So when you say 0 Kelvin, you're talking about minus 273 degrees. Because they wanted to get to the absolute limit. They wanted to be able to say 0 without having to go to minus 0, which is good. Next on, we're going to be going to the fact that from initial star to a red giant, it's much bigger. It's inflated and expanded to a much larger volume. So now that we have some key facts about the red giant, let's go on to our next star, which is the white dwarf. Now, once a red giant sheds all of its atmosphere, the only thing that remains is the core. And this remnant is called a white dwarf, which is usually the size of Earth, but hundreds, thousands of times more heavy and dense. Why is it dense? Because all this matter is compressed to an extreme degree, primarily due to something called the electron degeneracy pressure, which arises when electrons are packed so tightly together they resist further compression and form the negative pressure mentioned. If you watched our previous elementary particle video, you'll see that this relates to the Pauli exclusion principle. Electrons, or fermions, aren't sharing the same quantum state and giving out a negative pressure, balancing the gravitational force trying to suck all that matter, compress it in. And it's an outward pressure. And it's going to balance this inward gravitational force, of course. And this star, this white dwarf, is supported and stable, yet contains all that matter. However, if the white dwarf gains too much mass, above something called the Chandrasekhar limit, which is above 1.4 times the mass of the Sun, electron degeneracy pressure can no longer support it, may collapse more, and possibly form either a neutron star or a black hole. Here's a fun fact. A cubic centimetre of white dwarf matter can weigh 1 million grams. Wow. Another fun fact. After 10 billion years, approximately, the Sun will become a white dwarf. On to our next star, the neutron star. When a main sequence star, or white dwarf, overpasses the Chandrasekhar limit, as discussed, it runs out of hydrogen in this core. This is what happens next. The star will fuse to the helium, to carbon. But then there's a helium runout. The star will shrink and will then heat, and slowly you're going to need more fusion. So it's going to start converting carbon into neon, since it's heated after all that's come together, all that matter. And this is going to release energy. The process continues as the star converts neon to oxygen, oxygen to silicon, and eventually silicon to iron. The process will continue up to there, because these processes produce energy from keeping the star from collapsing. But each new fuel is only going to buy it less and less time. When silicon fuses into iron, instead of releasing energy and balancing that inward pressure, it's actually going to require energy. So the star will collapse because since the iron can't convert into a heavier element, it will then collapse and rebound, then send out a huge shockwave that will travel throughout the outer layers. The result? A huge explosion, a supernova. Before we go on to the next star, the red dwarf star, we're just going to quickly go over two types of neutron stars. We start off with the pulsars. These are rapidly rotating types of neutron stars. They have bright X-ray hotspots that form on the surfaces of the objects. And as they rotate, the spots spin in and spin out of view. So flashing, then stop, and flashing. It's really interesting. Next off, we have magnetars. This is basically a neutron star that has 10 trillion times stronger magnetic force than a regular magnet. 10 trillion times stronger than this magnet. That's amazing. And up to 1,000 times stronger than a typical neutron star. So that's really interesting, but now we're going to be going on to the red dwarf star. This is the smallest main sequence star, and is a fraction of the sun's size and mass. It's also the coolest, not the coolest in temperature, and more orange than red, just like the red giant. It's the most common star and makes up roughly 73% of all stars. Now, when red dwarfs produce helium via fusion in the core, the released energy brings material to the star's surface. Here it will cool and sink back down, taking along a fresh hydrogen supply to the core. Due to this constant process that's constantly happening, this churning, red dwarfs can steadily burn through their entire hydrogen supply for trillions of years. And this will have no change to the internal structure of the red dwarf star. Red dwarfs can live for 10 trillion years. And whilst they don't come after the phase of the neutron star, which eventually ends in a supernova, I thought it was important to include them since they are the most abundant star in the universe. They are main sequence stars, but really interesting on how they can last so long. In fact, we've suggested that possibly red dwarfs could have even started from the beginning of time and none have ever ended, most likely. But that's all for stars. I hope you really enjoyed this. This is the Shell Physics Show. I'm your host, Master Physics, and I hope you enjoyed.